This video will be the first of a series introducing the field of calculus, a huge and very important area of maths. We begin by carefully thinking about the notion of a gradient again. So we met this word when dealing with straight lines like this. And I'll tell you, for this particular line, it's got a gradient of 2. Now, what did that mean? When you first met this, you would have seen that it was some measure of slope or of steepness. By that, we would imagine if this was a piece of a roller coaster, which I'm really bad at drawing, so I'll just use this little pink ball here to represent our roller coaster. If we're traveling from left to right, the gradient is a measure of how steep your roller coaster is. Numerically, we measured the steepness by looking at what happens when you take a single step to the right. And then for this line, because its gradient is 2, it would mean that for each step to the right like this, we need to take 2 steps up. And this works, well, anywhere, and however long those steps are. So if we push the x value really far to the right like that, then to stay on the line, the y value would have to respond by increasing by double that amount, because the gradient is 2. Okay, so this was super helpful in calculating gradients, particularly when they were not nice numbers. You could pick any 2 points you wanted at your convenience, measure the vertical rise, measure the horizontal run, and you could recover the gradient by dividing those two numbers. Okay, so I'm sure you've seen this written as rise over run like that. And something we just barely touched on but will become super important as we dive further into calculus is this idea that the gradient is also measuring how y responds to a change in x. And we'll be using this sort of language a lot. Okay, so if x, the horizontal coordinate, were to be pushed along by some amount, then y, the vertical coordinate, has to respond by double that amount, as we said before. Okay, but again, it's just worth being very explicit with this idea, as we'll see soon. Okay, now when we did straight lines, we saw that the gradient was extremely useful. Okay, it gave you some measure of how fast a process was changing, and that in turn opened up a whole lot of useful stuff you could calculate or even predict at times. So the beginning of calculus is to think about how these really important ideas of gradient can translate to curves, to functions that don't just correspond to straight lines. So we still have some sense of slope or steepness, and we can get that by, again, placing our roller coaster model here. And if we were to ride this guy from left to right, then right now we know we're on a fairly steep uphill climb, in this orange direction here, and we can sort of intuitively see that this actually corresponds to the normal gradient of the tangent line at that point, this straight line that just touches the curve exactly once at that point. And I'll just tell you, this straight line just so happens to have a gradient of about 3, okay? It's positive because we're currently riding uphill. And we'll talk more about this tangent line later, it will be important, but for now I think it makes just as much sense to just keep track of the orange arrow, which has that gradient of 3 and a bit. Here's the problem though. As we travel along the roller coaster, our gradient will keep changing. So like here where it stopped, if you imagine you're riding this roller coaster, it wouldn't be as steep as it was just a few seconds ago. Numerically, the gradient has decreased to 0.84 or so. Okay, and you wait just a little bit longer, and now you're at the very top of the hill, where it makes sense to say that, well, it's actually flat there, it's horizontal. The gradient is 0 there. And then suddenly you start zooming downhill, so our gradient goes negative. It's negative 1.5, so maybe not quite as steep as when we first started, but it's still rolling down. And I think we get the point here, but just to finish it off, it eventually, well, flattens out again, and then it climbs. So here's our fairly shallow 0.84, and it's positive because we're rolling uphill, and then it shoots off and gets increasingly steep forever. So that's the main complication with the idea of slope or of steepness for a curve. It is always changing. And so for the first time ever, our gradient isn't just a number like 2 or 3 or -6 or something. It's actually going to be a formula, some sort of function that depends on x, I give you an x value, you give me back a gradient, that kind of thing. Okay, so we could ask now, how do we get this gradient? Well, does the idea of rise over run still hold up in this strange circumstance? Well, I just say it's still kind of true. Okay, it's still kind of true, because this complication is going to affect us in this calculation as well, and we'll illustrate this by pushing a copy of our roller coaster up to another point here to the end, and we'll think about measuring the rise and the run between these 2 points. And if we were going to simply divide rise by run as if it were a straight line, well, we would naturally have calculated the gradient of this red diagonal here. But I hope you can see that's not really that close at all to the gradient we're after, because we're after the gradient of the orange tangent line here, remember? Like that sort of steepness there. Okay, and so that's kind of wrong, okay, because our change in gradient has affected our calculation. We want to calculate a rise of a run between 2 points. But by the time we've moved at all from where we are, the gradient has changed. And in this case, it's become steeper, and that's made our calculation very wrong. The red arrow is super steep, the orange one we're after, not as steep. But here's the brilliant idea that the founders of calculus had. Remember, the problem was because the gradient's changing, right? By the time we've moved from one point to the next, it's changed on us, right? We can make our calculation better by simply reducing the amount we're pushing the roller coaster along. See, this is still not good at all, but it is better. If we move it even closer, then it gets even better. You can still tell that the red diagonal arrow is too steep, but it is more accurate than before. And so if we get real close here, for the sake of just illustration, I won't make the red diagonal get any smaller, or we'll stop seeing it very soon, but I will keep shrinking the other 2 horizontal and vertical arrows. We're going to slide the roller coaster closer and closer and closer until they're almost overlapping. Notice I say almost. That's because you can't actually make it exactly overlap, otherwise there would be no more gradient to measure, the whole picture would actually vanish. But I hope you can see that as I slid the right one closer and closer and closer, the red arrow got better and better and better, and maybe even now you can see, if you're on some super high definition device, that it's not actually perfect. We're like a pixel off or something. But if we can somehow calculate what that red arrow is doing, right, which direction it's heading towards, that will be our gradient. Okay, so that's sort of the plan here. We're going to still calculate some sort of rise of a run, but we're going to shrink those 2 things smaller and smaller and smaller. And so for the final point, the gradient is still tracking how y responds to a change in x. But now we know that we need to measure how y responds to a very small, an extremely small push to the x value. Okay, and provided the graph is nice enough for this to not mathematically fall apart, we will see that the response for y will naturally also be a very, very small amount. Okay, and it will still be by dividing these 2 tiny amounts that we can get a handle on what that exact gradient should be at that point. Okay, so to finish, just a quick note on language. While I'll still keep saying gradient every now and then to remind you that that's what we're doing, formally we save that word for straight lines. Okay, once it's on a curve, we tend to use the word derivative instead. Okay, so we'll say the derivative of a function, but really the derivative is just a formula that tells you the gradient of that curve at any point you might be interested in. That's where I want to leave it for now. Okay, our goal is to measure gradient, which on a curve will appear not as a fixed number, but as a formula, as something that changes as x does. And in order to get that formula, we're still going to use some kind of rise over run idea, only to make it accurate, we're going to need these rise and run numbers to be extremely tiny. Okay, so we still got a lot of work cut out for us, okay, but we'll tackle that over the next few videos. So thanks for watching, see you around.